Okay, let's get started. Good morning, everyone. Welcome to the GATE workshop, but the sixth international workshop on GATE estimation and prediction one. My name is Hyungjin Chang. I'm one of the organizers, and you hear me? Okay, good. So this is the opening remark. So GATE workshop has a very long history. So it first started in 2019 in ICCB. That was the very first GATE workshop. And at the time, there was no other, we have lots of workshops in computer vision area, community, but there was no single GATE related one. So we thought it's very big problem. And we could make the community contribution out of this like workshop organization. So we teamed up at the time, and now it's the sixth already. So I'm so proud that we have been acting as a kind of pivotal role for making all the AI-related or GATE-related researchers being together and share our thought, and then we also introduce our most advanced outcomes. So this is a big welcome from our workshop organizers, me, myself, Hyungjin, and also the Shuchong from Delft University, and also the Shalini and Tabo and Sonu, many others. And also, I'd like to give a big thank to our workshop sponsors. So NVIDIA and Google and the University of Birmingham, they are very generous sponsor for us. And thanks to their sponsoring, we could have our prizes for the best paper and best poster award. And also, we're going to host a workshop lunch at the end. So if you are interested to join, then feel free to come together. So this workshop, we have two excellent invite keynote talks and 4 peer-reviewed. It was very selective peer-reviewed workshop papers, and also we have invited 4 CIVOPR 24 paper presentations. For today, we have 2 invited keynote speakers, Professor Feng Xu and Alexander Fix. So it's going to be followed after this opening remark. And just a quick note that kind of tradition of the workshop from the very first series. And then we have a best paper award, which is prized by Google. And we have a poster session in 4th floor in the poster board. And you can see the poster number next to it. And we are going to give you the voting ballot for each. And then you can make a ranking by scaling. And then we're going to collect all the marks, and we will choose, we will select the best poster award at the end. So this is the workshop schedule. So following this opening remark, we're going to have 2 invited talks. Then the invited CIVOPR paper spotlight will be followed, which is 3 minutes each. There will be no Q&A session because right after that, there will be a poster session continued. So you can leave your questions to the author and you can have direct conversation. Then we will come back to here 11:10 to have the workshop paper presentation and this workshop 10 minutes of presentation and including Q&A. Then there will be award ceremony and the closing remark. Okay, I hope you enjoy this excellent workshop altogether. So the invited keynote speaker will be followed, and then the chair will be John.
Please, thank you. That's great. Okay, great. Welcome to the first session of the speaker, and we are very honored to have Professor Feng Xu as our first speaker. Professor Xu is an associate professor at the Tsinghua University. He also obtained his bachelor and as well as a PhD degree from Tsinghua University. Prior to joining Tsinghua University, he was a researcher at Microsoft Research Area. And Professor Xu's research interests include human body reconstruction, face animation, and medical image analysis. I'm looking forward to the talk. Good. Then I will switch.
Should I?
Just a second, please. Oops.
Okay, should,
It is. Okay. Professor Xu, can you speak something to test?
okay. So should I share my screen now?
Yeah, please share your screen.
Okay. And I'll play my slides.
It's just the desktop, not your slides.
Okay, so can you see my full screen slides?
Yeah, now we can do it. Yep. You can start. Thanks.
Okay. So, okay. Hello everyone. This is Feng Xu from Tsinghua University. I'm glad to have this opportunity to present our work here. And also, I'm sorry that I can't physically be there due to the visa problem. Okay, today, the title of my talk is eye region reconstruction with a monocular camera. Actually, it is not purely related to reconstruction, but also containing some other related topics. So digital human techniques are now changing our daily lives. They have many applications in movies, games, VAR, and even in the medical field, which I will discuss later. And some people say that eyes are the windows to the soul. So eyes play an important role in digital humans for creating realistic animation and for reflecting mental activities or some disease. Okay, to reconstruct the eye regions, existing methods can be roughly divided into two categories: high cost methods and low cost methods. The former usually depends on multiple cameras and controllable lightings. It can achieve high quality reconstruction, but it requires high-end devices and long processing time. Low-cost methods can work with a monocular RGB or RGBD camera, but usually generate low-quality results and have poor robustness. So in general, previous methods usually suffer from the trade-off between the capture costs and the reconstruction quality, and most of them do not consider the eyeglasses in the reconstruction. So as a unique accessory in the eye region, we consider the eyeglasses in two tasks. The first is to remove the eyeglasses in a portrait to generate a new portrait without eyeglasses. Actually, this is an image editing task and can benefit to some downstream tasks. And previous works may wrongly change the other face attributes while removing the eyeglasses. The other task is gaze estimation. Previous methods do not consider the eyeglasses refraction, which influences the gaze estimation for users with eyeglasses. So in this talk, I will introduce three works of my team. The first focuses on 3D face reconstruction with eyes, and we have applied it into the medical field. Then we study the techniques of removing eyeglasses influence for face portrait generation and gaze estimation. Okay, the first work is titled A Digital Mask to Safeguard Patient Privacy. So we use 3D face geometry reconstruction in face-related disease diagnosis. We call our reconstructed face digital mask. We divide the reconstruction of digital mask into 3 subtasks: face skin reconstruction, eyelid reconstruction, and eyeball reconstruction. Correspondingly, we involve face, eyelid, and iris features for the optimization of each subtask. In face reconstruction, we use a parametrical bilinear model that contains identity and expression dimensions. Given different identity and expression vectors, the model generates different shapes and expressions of human faces. Here, maybe I can use the laser point. Okay. So here, WID stands for the identity vector, and WEXP stands for the expression vector. Okay. So with the help of the detected face landmarks in images, we optimize the vectors by aligning the projected points of the face model with the detected face landmarks. Besides the identity and expression vectors, we also optimize the global scale, translation, and rotation of the face model. So this is for the face skin region. And in eyelid reconstruction, the eyelid model is a linear model with a mean geometry and a set of shape bases and motion bases. So here, this MOE means the mean geometry, and MIES means the shape basis, and MJEM means the motion basis. Okay, so similarly, we are given different shapes and motion vectors. The eyelid model can synthesize different shapes and motions of eyelids, and this equation shows how to synthesize a particular eyelid using this eyelid model. Okay. Similarly, with the help of the eyelid landmarks, we can optimize the eyelid parameters by aligning the projected points of the eyelid model with the detected landmarks. But different from face reconstruction, the detected eyelid landmarks are too sparse to fully constrain the optimization. To solve this problem, we involve an eyelid edge detection method to densify the eyelid landmarks using curve fitting. And then we do the optimization similarly with what we have done with the face model. Okay, and finally, we handle the eyeball. In eyeball reconstruction, we first involve a 3D eyeball, and we use eyeball calibration to get the iris size, eyeball radiance, and eyeball positions in the skull. Then we fix these values in a video sequence and only optimize the eyeball rotation in each frame, also by aligning the projected iris points of the eyeball model with the detected landmarks on the images. And now we can see the result. So finally, by merging all the reconstruction results, we achieve full face reconstruction with eyes. As the reconstruction is based on sparse parameter optimization, the whole process can run in real time. So here we show a live demo of face reconstruction. Okay, so then we apply the 3D face reconstruction technique to the medical field for privacy protection in the diagnosis of some eye-related disease. We know that facial images contain disease features which are useful for diagnosis, but they also record identity information which causes patients concerns about their privacy. To enhance their willingness to use facial data in clinics, it's necessary to disentangle the identity and disease features of facial images. Digital mask only contains facial geometry information, but remove the textual information. so it can be used for diagnosis, will protect the privacy of the patient. Okay. Specifically, we focused on four ocular disease, which involve 10 abnormal behaviors. So here we show those abnormal behaviors in those images. To verify the ability of digital mask to retain disease features, we asked 12 ophthalmologists to diagnose patients based on either the original face videos or the reconstructed digital mask videos. So here, these are some images of our digital mask videos, and compare their diagnostic results. The kappa values on the four ocular disease are all greater than 0.8, which represents high diagnostic consistency between the two kinds of videos, and indicates that the ability of digital mask to retain disease features. Okay, and to verify the identity removal ability of digital mask, we perform a user study where, given a rendered digital mask or a cropped face image, participants are asked to choose the corresponding patient from 5 candidates, as you can see here. And in the right figure, we can see that cropping presents over 90% re-identification accuracy, while our technique reduced it to 27%, which shows the strong identity removal ability of our technique. So here we show two clinical examples of our digital mask. The right is the digital mask result, and the left shows the patient to be diagnosed. Okay, so this is the first work, and the second work aims to remove eyeglasses to generate eyeglasses-free facial portraits. The title of this work is Portrait Eyeglasses and Shadow Removal by Leveraging 3D Synthetic Data. A large portion of people wear eyeglasses in their daily lives. In their portraits, eyeglasses sometimes bring unwanted occlusion and cast shadows on faces. These effects also lead to inaccuracy in many downstream tasks, including eye region reconstruction, as I mentioned before, as well as some image-based techniques like face verification, expression recognition, fatigue detection, and so on. These motivate us to remove eyeglasses and their shadows from portraits. However, completely removing eyeglasses suffers some challenges. First, we need to consider the complicated lighting effects. Second, to use a supervised learning to train a model for eyeglass removal, we need paired data of a user with and without eyeglasses, which is difficult to collect. To solve this problem, we propose a novel segment Zen removal network for both eyeglasses and shadow removal. As real data is difficult to collect, we generate a high-quality synthetic data to provide supervisions for network training. And to fill the gap between the synthetic and the real data, we introduce a cross-domain segmentation module to enhance the generalization capability on real portraits. So our synthetic data is generated by 3D rendering. For 3D eyeglasses, we ask professional artists to create 21 eyeglasses models. So even though 21 is not a big number, we find they are enough for most eyeglasses in our experiments. And for 3D faces, we directly use the face scan dataset collected by Wang et al. Okay, so then we align the eyeglasses with faces automatically by some heuristic rules, and the details can be found in our paper. So after this alignment, we get the skies with glasses, as you can see here. And then we use HDR lightings to render the sky with eyeglasses, and we generate 4 synthetic images and 2 segmentation masks. So the 4 synthetic images enumerate the visibilities of eyeglasses and shadows, which provide supervisions for our networks used for eyeglass and shadow removal. And the 2 masks of eyeglasses and shadows can provide supervisions for mask prediction. So we divide our task into 2 stages. First is for mask prediction, and the second is for the item removal. Okay. And in the mask prediction stage, a domain adaptation network is applied to bridge the gap between real and synthetic data. So to be specific, we apply adversary learning to find a uniform feature domain, and then predict eyeglasses and shadow masks based on the features. As shadow is caused by eyeglasses, so we first predict the eyeglasses mask and use it to help the shadow mask prediction. So as you can see here, we first predict the eyeglasses and use the eyeglass mask as input to predict the mask of the shadows on the face. And here we show the training losses, and details about the training can be found in our paper. So in the item removal stage, the next stage, we apply an inverse order that first remove shadow and then remove eyeglasses. So you can see here, we first remove shadows on the face, and then we remove the eyeglasses to get the final result. So here, to enhance the robustness, we adopt a mask operation to set the pixel values of eyeglasses regions to 0 before the D-glass network. This operation can improve the generalization capability of eyeglasses with unusual textures. So here you can see that we set, so here we just set grid values to the eyeglasses, but in our method, we set the glasses with 0 because we have already get the mask of the glasses. So we can set those pixels to 0 before we do the glass removal. Okay. And finally, we show some result. We evaluate our method both quantitatively and qualitatively. And the FID and face recognition metrics in the left table show that our method can generate photorealistic results and have the ability of identity preservation. And in the right figure, compared with previous methods, our method have obvious improvements in removing sharp shadows, as you can see here on the right side. And we remove sharp shadows as well as eyeglasses with unusual shapes and textures. And I think more results can be found in our paper. Okay, the third work considers eyeglasses refractions in appearance-based gaze estimation. And the title of this work is Towards Eyeglass Refraction in Appearance-Based Gaze Estimation. So gaze is an important clue to reflect human intentions and mental activities. Estimating gaze accurately is significant in many applications like human-machine interaction, driver monitoring, after animation, and even medical analysis. Appearance-based gaze estimation usually takes full face or eye region images as input and outputs 3D gaze directions or 2D gaze points. It has made a rapid development in recent years with the help of deep learning techniques. So however, previous works do not consider the eyeglass refraction. They just mix glasses and glasses-free samples together to train a network. But in our work, we believe it harms gaze estimation, and we aim to find a better solution to consider the eyeglass refraction in gaze estimation. So our work consists of two main parts. The first part is about the theory of the refraction effect and its experimental validation. As the previous works haven't discussed the refraction effect, we designed some experiments to demonstrate it. In the second part, we explicitly consider this effect and improve the performance of gaze estimation networks. So before we talk about refraction effect, we first review the data collection pipeline for traditional appearance-based gaze estimation. Okay, at the beginning, the participant is asked to focus on a gaze target X, as you can see here. Then the image is recorded by the camera, okay? And the ground truth gaze is defined by the vector from the eyeball center position O to the point X. Then neural networks are expected to learn the appearance gaze mapping. So we use neural network to learn this mapping. So however, is it will pose the problem? So we believe the answer is no, considering the same gaze target X. So what will happen if we look through myopia eyeglasses? Actually, according to physical laws, in this situation, the eyeball rotation would be smaller than a naked eye due to the light refraction through the lens. So we can see here, actually, the eyeball is focusing on the point X, but due to the light refraction of this lens, it seems that the eyeball is facing to another virtual point Y here. So this is the situation for the myopia eyeglasses. And similarly, for hyperopia eyeglasses, the eyeball rotation is expected to be larger. As you can see here, the virtual Y point is on the other side of X compared to the previous situation. So this introduces ambiguities because it leads to many-to-one appearance gaze mapping, which is difficult for network to learn. So now we know the problem we want to solve. So next, we want to do some experiments to validate the accuracy of this theory. In order to visualize the distribution of eyeball rotations for glasses and no glasses samples in public datasets, we propose a specified gaze representation, and we call it RCR, relative coordinate representation, which is defined as the 2D relative position of iris to the eyeball center, which is calculated by the positions of the corresponding landmarks. So we can see here the green point stands for the eyeball center, and the orange point stands for the iris center. And these are both 2D points, which is projected to the 2D images. So this vector stands for our relative coordinate representation. Okay, so RCR is a kind of gaze representation, excluding some other effects like illuminations, skin colors, and so on. So we will use this RCR to evaluate our theory. So as a result, we can get the distribution of RCR for a public data set as shown in this figure. As we can see, the glass samples in red are covered by non-glass samples in blue. So in this figure, actually the x-axis and the y-axis stands for the x and y values of our RCR. So here we can see the glass samples have smaller x and y values than the non-glass samples. So we can see the distribution of those points. And we believe this is because almost all glasses subjects in the dataset were myopia eyeglasses. So when they focus on the same gaze targets, their eyeball rotations tend to be smaller. So their X and Y values are smaller than the non-glass samples. So however, the subjects in public datasets only have one wearing conditions. Which means the result may be mixed some other factors like identity. So it's also possible that so all the samples with glasses, they always focus on some points on the frontal side, and the samples without eyeglasses, they focus on some points on the sideways. So this is another explanation of this result. So this result is not very solid. So we want to develop a more solid experiment. So the more solid experiment is like this. To further exclude the influence of identity, we collect a new dataset by ourselves, in which each subject has both glass and no glass data. So in detail, for each subject, we collect 3 frontal view portraits, 2 non-glass portraits, one for training and the other for testing, and 1 glass portrait for testing. Okay, and use the training data. We train a small MLP to encode the gaze mapping for naked eyes, and validate the learned mapping on the 2 test sets. Taking a myopia subject as an example, we compare the results on the 2 test sets. The top figure shows the result for the non-glass test set, while the bottom figure shows the result for the glass test set. The x-axis shows the ground truth gaze rotation, and the y-axis shows the predicted gaze rotation. We can see that the non-glass result is better than the glass result, which is obvious because we use the non-glass data to train the model. One important thing is that for the result on the glass test set, the derivation has an obvious bias that the result tend to be smaller. So you can see that the result tend to be smaller, which is consistent with our theory for myopia eyeglasses. So then as we know the ground truth diopter of each subject, we can correct the gaze result with the known lens parameters. And after the correction, the glasses result becomes comparable with the non-glass one. This further validates that the previous derivation is mainly caused by eyeglass refraction. And here we just show how to do the correction, and the details can be found in the paper. Now we confirm the refraction effect, but how to solve it? Although the aforementioned correction can address this problem, it is not suitable for real-world application as it needs the diopter as an additional input. We hope that our method can improve the performance without additional inputs or assumptions. To achieve this, we propose a multitask framework to consider the refraction effect for general inputs. In detail, apart from gaze estimation, we ask the network to classify the wearing conditions at the same time. So it is an additional binary classification task. This task helps the network to automatically recognize the eyeglasses in the images. As most glasses subjects in public datasets wear myopia eyeglasses, the eyeglass information can help the network to do something similar to the correction and thus performs eye gaze estimation better. So to validate its effectiveness, we do the comparisons between our multitask framework and the baseline with different network backbones. Here, the baseline is a single task framework. We train the networks on 2 data sets and make a cross dataset validation on the other 3 datasets. So the results show that by introducing variant classification as an additional task, the networks have generate general improvements on different baselines. So we can see that the numbers in red is better than the numbers on top of them. And also outperforms another multitask setup with gender classification as an additional task, which means glasses have stronger influence on gaze estimation than genders. To explore the reason of the improvement, we visualize the image features learned by the 2 frameworks using TSNE. As shown in the figure, we can find that the image features of the baseline are mixed together for both glass and no glass samples, while those of the multitask framework are separate, which means the multitask framework handles the 2 kinds of data differently in gaze estimation. And thanks to the distinctive features, our method benefits not only the glass samples, but also the non-glass samples. So finally, let me conclude the talk. First, a high-quality reconstruction method for eye region is not only useful in computer graphics, but also valuable in more broad fields like medicine. For better eye region reconstruction or some other face-related tasks, eyeglasses can be naturally removed to get an eyeglass-free portrait. And optical rules need to be considered for more accurate gaze estimation. Okay, that's all for my talk, and I would like to thank my collaborators and founders, and I also list my papers here. Okay, that's all for my talk. Thanks.
Great, wonderful talk. And I want to ask if anyone have a question, and if you have a question, I ask you come here to ask a question, please. Okay.
There's a question on the Eric.
Hi, can you hear me?
Yes.
Yeah. Okay. I just have one question. Great talk. I was wondering for your eyeglasses removal part of the talk, did you also add any optically active material in your synthetic eyeglasses so you can remove these refraction effects from or reflections and so on using your network? Or did you not try that?
We haven't tried that. Actually, currently, the synthetic procedure is quite simple. We just put the eyeglasses on the face. And maybe we can handle this somehow because we have the adversary training to fill the gap between the synthetic data and the real data. But we not explicitly do this. So I think maybe in the future, if we have involve all the things into our synthetic pipeline, the synthetic data will be more realistic, and I think the result will be better than the current version.
Thank you.
Okay, thanks.
Hey, great talk. So I really enjoyed that. This is Alex. I'm speaking next. So I had a question about the correction for wearing glasses, and you talked a lot about how when the user's view of the world is refracted, so that causes their gaze angle to actually be different, but also the camera is looking back through the glasses, and that obviously also changes how the gaze tracker sees the eye. And I guess my question is how you can disentangle those 2 effects, or whether it even makes sense to try. Maybe it just makes sense to train a big model that does it, but maybe there is something we could do to disentangle them.
Yes, that's really a good question. We know this, but we haven't handled this. So when we do this task, we also notice that there is another distortions. Maybe we can call it distortion. need to be considered. But actually, we found it's not influence the result too much. So in our experiment, we totally ignore it, and we can evaluate our theory, and we can also use the multitask training to improve the result. But I agree that this is also needed to be considered if we really want to do a very accurate gaze estimation. Yes, this is an important thing.
Great, thanks.
Another question from the audience? I have a short one. I want to ask for your first work, is that you consider lighting condition is one factor when you do the 3D reconstruction with face?
Actually, we use face landmarks to reconstruct the face, and when people train the networks to do landmark detection, they collect data of different lightings and even some challenging lightings. So the landmark detection performs well for different lighting conditions. So if the landmarks are correctly detected, the reconstruction can be correctly performed.
So your accuracy rely on the landmark detection at the first place. That's
Yes,
correct.
exactly.
Okay. Yeah. Thanks for your answer. Okay. Yeah. Please.
Hello, this is Dominic. I have a question concerning your data acquisition. You said you collected a data set yourself. How did you get the coordinates of the eyeball center? Did you estimate it with a kind of distance estimation with the landmarks, or do you have a laboratory scenario where you measure everything for a couple inches or 1 inch?
Okay, so actually we do a eyeball calibration, and I think we didn't do it very accurately. We just record some videos of the face, and we ask the user to focus on some points with known coordinates, and we optimize the eyeball center position and some other parameters, because we can record many frames, and so we can have many constraints, so we can solve those parameters.
Thank you.
So that's what we have done. Am I answering your question?
Yes.
Okay.
Okay, if there are no more questions, let's thank the speaker again.
Thank you. Okay.
Good. Then we'll have next
Yeah,
speaker. You can set up in the meanwhile. Oh, yes. That's a good reminder. Now. Oh, Let's open. This one, yeah. Let's do it. Hopefully it works. Maybe I do something else. Good morning, everyone. And today I will introduce my work. What do you see in vehicle? Comprehensive vision solution for in vehicle gaze estimation. And I'm Yihua. Sorry, I need to. Here it is. Okay. And I think the intelligent cabin is a hot topic. And in the intelligent cabin, we are focused on the safety, interaction, and the vehicle entertainment. And for the three application, the human perception is a very key technology. And for the perception, we need to capture the voice, gesture, and gaze. And for our work, we propose a method for the in-vehicle gaze estimation, and this is the demo for our work. We collected the data in the vehicle, and our contribution contain the four contributions. The first is a data collection solution for the in-vehicle collection, and we collect the first data set and propose the method for the gaze direction estimation, and we extend our method for the gaze room classification. And about the challenge, I will briefly introduce it. And I think the biggest challenge is the data adaptation in the vehicle and how to annotate the gaze direction in the vehicle environment. I think some method like to perform the gaze room estimation is very easy to annotate the gaze room. And some method use the model-based gaze estimation, so they can just capture the people and the eye landmark. And some method like to collect the data with eye tracker, but of course it will make the image contain the glasses. And for our method, we use the driver monitor camera in the vehicle, and this is the picture inside the vehicle. And we collect a data set, and for the detail of the data collection solution and the data collection process, please refer our paper. And we also propose a method for the gaze direction estimation. And we focus on two aspects. The first is the multi-level feature. We use the multi-level feature to make the network focus on the eye region. And we need to use some specific loss function to make it work. And the second is the virtual dual camera. Like we perform the perspective transformation on the image, and it also called as data normalization. And we use the original image and the normalized image to build the virtual dual camera. And we define the camera pose to integrate the two features. And we also consider the gaze room classification. And in the vehicle, we cannot compute the intersection between the gaze direction and the vehicle model. So we propose to define a basis triplet and to extract the positional feature from the projecting point. And we add the module to our network. And we use the visual feature from image and the positional feature from projection to estimate the gaze room. And this is the experiment. Our method can get the best performance. And this is the experiment to demonstrate the advantage of our the multi-level feature. And this is a blind study for the multi-level feature and the dual camera setting and the visual feature and the positional feature. Okay, thanks. And if you want to know more about my work, you can come to the post session in tomorrow morning. Okay.
So the question, you can ask a question in the post session, if the problem is right after the session.
Our next talk will be given by Jinzhou, and the work is titled as Learning from Our Days, Clear Attention Prediction Oriented by the Evolution.
Oh.
This one.
Oh, okay. Thanks for you.
Okay, hello everyone. Thank you for joining me today. My name is Yusheng Zhou and PhD candidate at Swansea University in China. Today, I'm excited to present my recent work, learning from observer gaze zero-shot attention prediction oriented by HOI recalculation. So first, let's rethink sinus prediction. Prior effort has focused on predicting attention accurately, but often overlooked to apply human gaze information to broader computer vision tasks, like understanding or generation. So in the other hand, for action understanding, particularly in HOI, there are significant challenges in capture diverse and subtle action feature, and incoherent attention often land in coherent understanding. So in this work, we explore a bidirectional connection between synesthesia and action understanding. We let action understanding drive synesthesia prediction and then feedback to action, promoting mutual improvement in both fields. Specifically for gaze recognition dataset, previous work focused on instance level, emphasizing foreground human and object, but often overlook the interaction-centric gaze, like smelling, eating, hugging, driving, which involve rich human knowledge of understanding action. Therefore, we introduce the interactive gaze dataset, which uniquely captures the visual attention of human observer during the understand HOI. Our data set includes 6,000 scenarios, cover 714 HOI category. You can download our data set via this QR code. Secondly, we design a computational model to mimic the mechanism in interaction-oriented attention. Give a sample of HOI pair. Our goal is to generate an attention heat map that reflects key vision cube of HOI. So we propose interactive attention model, which is divided in 3 parts: empirical logic representation, cognitive goal modeling, and progressive understanding. Extensive experience demonstrates that our proposed IA model outperforms SOTA sentencing method in both zero-shot and supervised setting. Furthermore, we are introduce a general and effective HOI training strategy that can be applied to most HOI model with attention supervision. Remarkably, we find that applying limited human attention from IG dataset enhance the performance and interpretability of SOTA HOI model. For example, with MUIN, you can see it is an HOI model published at CVPR 2023. We can see that incoherent model attention than the incoherent reasoning result. But after aligning our intention-oriented attention, the reasoning results are coherent, and the model attention become more focused and interpretability. Moreover, we discovered that aligning attention generalized by IA model further enhanced HY detection, surprising the performance achieved using real human attention from IG dataset. So, in summary, in this work, which has built connection between science and action understanding through three main contributions: introducing an gaze fixation dataset, an attention prediction model, and a novel HOI training strategy. Thank you for your attention, and I'm currently seeking a position as a self-funded visiting student for 1+ years. My research not only on gaze, but also on HOI, autonomous driving, and the AOM application. If you are interested in my work, please reach out to me. Thank you once again. That's all.
Next, we will have a presentation from Sammy. The work is titled Sharing in a Transformer Architecture for Multi-Person Based Learning.
So hi everyone, and welcome to this presentation about Sharingan. So this paper is about a task that's a little bit different than what was presented so far. So the gaze following task in computer vision is basically where we have an input image from a third party perspective and a head box coordinate for a person. And what we want to do is basically predict the yeah, and what we want to do is basically predict the 2D location of where the person is looking in the image. In practice, however, what we predict is actually a gaze heat map and use the argmax of that to derive the gaze point. Optionally, we can also predict a binary flag that denotes whether the person is looking inside the scene or outside. So previous methods proposed for this task are basically single person. And what this means is that they require multiple forward passes in order to get the results for all the different people in the same image, which leads to wasted computation, basically. Also, most of these methods focus more on the design of these person gaze representations and how they interact with the scene, but pay very little attention to the decoding mechanism afterwards that is used to get the final heat maps. The usual decoder design is basically a stack of transposed convolutions operating on very low dimensional feature maps, which leads to predictions forced on coarse information. So we're going to try to address these two challenges. Our proposed architecture is basically a hybrid CNN transformer. So the scene image is converted first into these image tokens. Second, since we have these additional inputs, namely the head props of different people and their corresponding head box coordinates, we need a way to efficiently encode them into the architecture. We find that compressing this gaze directional information that we get from the head props, as well as the head location information into these single gaze token representations, not only works very well, but also allows us to accommodate multiple people in the same encoder step with minimal extra costs. So how do we get these gaze tokens? Well, essentially, the head props are passed through a CNN backbone, followed by a projection in order to get the gaze token. We add to those gaze tokens embeddings on the head bounding box coordinates in order to make them aware of the position of the person in the scene image. Optionally, we can also append an MLP regressor to these intermediate gaze embeddings in order to predict a 2D gaze direction, which can be useful in certain cases. In terms of decoding, we take these intermediate representations from the VIT layers and pass them to our conditional DPT decoder in order to predict the gaze heat maps. More on this in a minute. Finally, we concatenate the input and output gaze token for every person and pass them to an MLP classifier to obtain the final in versus out probability scores, so whether the person is looking inside or outside. Now we talk about the conditional DPT, which is basically a lightweight multi-scale decoder whose goal is to improve the gaze decoding mechanism by leveraging more fine-grained information from the scene. The design is basically inspired mostly from the traditional dense prediction transformer, where the idea is to take tokens from intermediate layers of the PIT and reshape them into feature maps, spatial feature maps of different simulated resolutions and progressively fuse them. So one major difference with the traditional DBT formulation is that in our case, we need to decode multiple heat maps using both the gaze tokens and the image tokens. So how do we do that? Well, our major change lies in this reassemble operation, where we first take the image tokens, project them, and reshape them into spatial picture maps, and then we duplicate them, right? And we multiply each one with the corresponding gaze token to make them person-specific. And this is what is used to decode the gaze heat maps for every person. The final fusion operation remains mostly unchanged, where we combine feature maps from the current and previous levels and then upsample to a higher resolution. So our extensive experiments show that we obtain very strong results on all three available benchmarks for this task, although we are also able to support multiple people at the same time. So compared to previous literature on method, I'll propose most of them, even those using multiple modalities or using a single person.
Thank you all for continuing. So we're going to continue on with our program. And next, we're going to have all the oral presentations for the papers that have been accepted to this workshop. So first up, we have Swati Jindal, and she will be presenting her work on spatial-temporal attention and Gaussian processes for personalized video gaze estimation. Okay, Swati.
Hello everyone, I'm Swati and today I will present my work on spatial temporal attention and Gaussian processes for personalized video gaze estimation. This work is done during my PhD at UC Santa Cruz with my professor Roberto Manducci and a collaborator Mohit Yadav. So in this work, we propose a video gaze estimation model where we have to predict a sequence of gaze directions from a sequence of input RGB frames and capture the dynamics of the eye movements using this sequence to sequence model. So what are the challenges that comes when we go from the image input to the video input? So you can see in this sequence of frames, there is a person moving in the background, and also the expressions of the person in the main frame for which we want to detect the gaze are changing. So these changes, they are not important for our main task of predicting gaze direction, and they can act as a distractor for our actual task of detecting eye movements. So through our proposed framework, we kind of want to suppress this suppress these distractors and highlight the relevant changes specific to the eye movements or like head pose movements or any changes that are good for our task. So this is the overall idea of our proposed framework called spatial temporal attention for gaze estimation, shortened for STAGE. So so it consists of three main components. First is the feature extraction component, where we take a sequence of input frames and pass it through a common shared ResNet model, which gives us the 2D feature maps for each of the frame. And then it is passed through spatial and temporal attention modules, which I will talk further in my slides. And then our output, we have a gaze prediction layer, which consists of an MLP block, again shared among all the timestamps, and give us the two Euler angles, pitch and yaw for each gaze direction. So again, I mentioned the motivation behind the SAM module, which is spatial attention module, is to capture the relevant changes, which is like highlighted in the green boxes here, which is to detect the eye movements, eye movement change that is occurring between these two consecutive frames. and suppress the changes which are irrelevant. For example, like the highlighted in the red box, which is like background movements and the expression changes. So because so in the SAM module, we are passing 2 consecutive frames as an input. Because we are using these 2 consecutive frames as an input, only as an input, so it kind of captures the local dynamics that has like local changes that has occurred between these 2 consecutive frames. So SAM captures these changes that occurs between these 2 frames and embeds that changes into the output D-dimensional feature vector along with the RGB information. So in our framework, we have designed 3 kind of SAM variants: dual, cross, and hybrid. So the dual SAM is, okay, I have a, okay, dual SAM kind of takes the feature extracted from the ResNet, and it kind of detects the 2D attention map for each of these frames, and it compares these 2 attention maps. So if these attention maps are very similar, it means there is not much change between these 2 frames. And if these if these attention maps are very different, it kind of embeds the change that has occurred into the output feature vector along with the RGB information. Because dual SAM uses the whole 2D attention map as an input to compute this change. So it learns static attention, and it is effective in capturing only a single change. So in the cross SAM, we kind of do the patch-wise correlation where we compare each patch in one frame to the each patch in the another frame, and see what changes has occurred using a cross attention transformer block. Because we are comparing each patches in these 2 frames, it is capable of capturing multiple changes, and it learns the dynamic attention between these 2 frames, and it embeds those multiple changes into the output feature vector. In the hybrid SAM, we combine the strengths of both of these SAM variants, dual SAM and cross SAM. As I mentioned before, the cross SAM is capable of highlighting multiple changes. So cross SAM kind of embeds all the multiple changes that has occurred between these 2 frames. For example, they can be eye movements as well as the expression movements in the same consecutive frames. So it kind of highlights these 2 changes occurring in these 2 frames. And then task of dual SAM is to highlight the most relevant change, for example, like eye movements for our task. After the SAM module, we have temporal sequence model, which takes care of the long-term dynamics of eye movements. Because SAM was capable of capturing only the local dynamics, the temporal sequence model is capable of capturing the global dynamics of these eye movements. So we experiment with 2 variants. One is unidirectional STM, and another is causal transformer decoder model, which is like similar to GP2 model. And we mask any future information that comes from this sequence for every timestamp. So at the output, we have gaze prediction layer, which is again formed from the fully connected layers, and it is shared among all the timestamps. And it outputs 2 Euler angles for each timestamp. Here are a few results on the quantitative analysis when done on the within dataset evaluation, where we train and test on the GAZE 360 dataset. And here I'm just showing 2 baselines as ResNet flatten and residual concat, where we do not use any SAM module. We just flatten the features from the ResNet model and pass through the transformer through the temporal sequence model. And then from the residual concat, we concatenate the frame differences between consecutive frames as an additional channel to the RGB frames, and again flatten those features to pass through the temporal sequence model. And we do ablation on the different types of SAM variants, and we see that hybrid SAM performs very well among all the SAM variants as well as from the baselines. Here are some qualitative results where we superimpose the attention maps learned from the hybrid SAM on the 2 consecutive frames, which were passed as an input to the SAM module. So on the left side, you can see there is a background motion that has occurred between these 2 examples. Again, like through the SAM module, we are enabled to highlight only the eye regions that is important for our task. And on the left, on the right side, you can see the expressions of the person are changing, and still we are able to highlight the eye regions. So after we do this stage model training, we personalize it through the GP-based corrective, and we learn the bias correction for these two Euler angles using GP-based model. So GPs are capable of giving us the mean and variance estimate. So variance is important estimate for gaze tracking, especially for critical applications like self-driving. So once we have this uncertainty estimate along with the mean, we can filter out the uncertain predictions, mainly for example, you can see here blinks and all the extreme head poses, they come under the category of uncertain predictions through our model. Thank you, and you can check the GitHub code for our and paper for more details. Yes.
The computational complexity compare between the spatial attention module and the rest of it? Like 1x bigger, 10x bigger comparison.
So in the cross-SAM specifically, we are using attention model. So that might be very computationally, not very, because it's a very fixed sequence length, because we are doing patch-wise patch correlation. So it depends how many layers and you use, but it should not be a lot different if you're just using one layer transformer model. Yeah, but if you're getting good accuracy, I think there are methods to decrease the computational complexity for the transformer model. Yeah.
All right, cool. So let's thank the speaker. Okay. So next we have exploring the zero-shot capabilities of vision language models for improving gaze following by Anshul Gupta.
Thank you.
Hi everyone. My name is Anshul, and today I'll be presenting my work on exploring the zero-shot capabilities of vision language models for improving gaze following. So as Sami mentioned previously already, the gaze following task involves predicting 2D gaze targets of a person in an image or video. So in this case, for the person on the left, it's the person on the right. This can be used for social gaze, for example, looking at other humans, looking at each other or eye contact, and gaze towards objects. This has several important applications, for example, in healthcare for psychiatric assessment, in retail for understanding product preferences, or in robotics for understanding human-robot interaction. In general, gaze following is a fairly complex task. It requires understanding both the person and the scene. So you need to understand the person's field of view, their gaze direction. You perform 3D reasoning about what's towards the front of the scene, what's towards the back of the scene. And you also need context. So you need to understand the person's posture, salient items present in the scene, relationship between people, how they're interacting, and so on. In the past, works have leveraged dedicated view extraction methods such as pose or depth information for improving performance. Indeed, you see this image on the screen where we leverage pose and depth information for gaze following. However, this means that we need several models for all the different cues that we would like to consider, which starts to get computationally expensive, or we might not even have the necessary models for the different cues that we care about. Recently, vision language models have shown impressive zero-shot performance for several tasks, such as action recognition, classification, and so on. So we wanted to explore whether VLMs can reliably extract gaze-relevant contextual cues, and how to incorporate these cues and actually improve gaze following performance. So as a quick recap for how image-text matching works in VLMs, you first have a visual prompt that is passed through an image encoder to get a visual embedding, and you have a text prompt that passes through a text encoder to get a textual embedding. We then perform a dot product between the visual and text embedding to get a score for that particular cue. In this work, we focus on person-related contextual cues, such as those involving pose, example, Alex sitting or standing, person-person interactions, such as speaking and giving, and person-object interactions, such as reaching or manipulating the object. This means that we need to focus on a specific person in a scene with multiple people. And to do that, we perform visual prompt engineering by drawing a red circle around the person of interest, graying out the rest of the scene, blurring out the rest of the scene, etc. And we apply this either over the whole image or the person prop. We found that drawing a red circle over the image gives the best performance, which suggests that having the extra information coming from the rest of the scene helps better understand the cue. For the text prompting, we perform a template-based approach. So we have a template such as person as class, and we replace the words person and class with the relevant synonyms. For example, a human is sitting. We find that ensembling over all the possible templates and synonyms actually gives the most robust performance. In terms of results, we see that the VLMs are able to capture cues that are common and more statically recognizable. For example, standing and talking to, whereas we don't get such good performance for cues that are less present in the data. Overall, BLIP2 has the best performance among the VLMs. We also performed some initial explorations on in-context learning to see whether that can improve performance, and we do see some benefits. However, this is much slower during inference, so we don't adopt this approach for the next part. So for the next part, you want to see whether actually incorporating the predicted cues can improve gaze following performance. And for this, we leverage MTGS, which is a recent temporal architecture for multi-person gaze following and temporal gaze prediction. Importantly, it allows for the seamless integration of auxiliary person information. So in this architecture, we first process the set of frames to obtain frame tokens encoding scene content. We then process the head crops to obtain person tokens encoding gaze direction. The person tokens, the scene tokens interact through self and cross attention layers to update these tokens. And finally, all the tokens are decoded to predict person-wise gaze heat maps and pairwise social gaze. To incorporate the VLM context information, we update the person tokens, and I'll explain that in the next slide. So the way we update the tokens is to first take the set of Q scores from our VLMs and project it using a projection layer to obtain person context tokens. These are then added with the corresponding person token to obtain the updated set of person tokens. The rest of the architecture then follows as usual to get the gaze following and social gaze predictions. In terms of results, we see not much improvement for on gaze follow for within the dataset performance, and we attribute this to the lower resolution images in that dataset and the fact that the annotations are less reliable and thus the metrics are less reliable. And in general, the scenes are also quite simple with a single salient target. In terms of cross-dataset generalization, we actually see improvements. It suggests that Q extraction is robust across datasets, and we see large improvements when considering more Qs. And this is quite interesting because adding more Qs does not actually have much impact on compute time, because we can extract all the textual embeddings at the start and then perform a dot product with any new image that comes. Here are some qualitative results. On the left, we have the image with no context, and on the right, we have the image with context. And we see that for person number 2, for the top image, it makes an error initially, but when we add contextual information, such as the fact that this person is holding this child, it's actually able to make the right prediction. Similarly, at the bottom, for person 3, we have a wrong prediction, but when we have contextual information, such as the fact that the lady is talking, it makes the right prediction towards person 1. And here is also a video of qualitative results. We see that in general, the model is performing quite well in terms of gaze following and social gaze predictions. LAH indicates looking towards another human, and LEO indicates eye contact while looking at each other. On the right, you see the top predicted VLM scores, and it captures different aspects such as watching or maybe reading and so on. In conclusion, gaze following requires person and scene contextual cues, and VLMs can, in fact, extract person-related contextual cues, such as, and the red circle of the image is the best visual prompt, and sampling over text prompts is the most robust way. Text prompting, BLIP2 has the best overall results, and in-context learning can further improve performance. We also see that extracting these cues in the gaze following model can improve generalization, especially when we consider a large set of cues with negligible impact on compute time. In terms of future directions, we want to explore other prompting schemes, including learnable approaches, other VLMs, including video-based VLMs, and actually trying to distill the VLM information into the gaze following model. So that way, we don't need to perform two separate passes of the VLM and the gaze following model. Thank you.
Okay, we have time for a few questions.
I want to ask you, in the model, you detect n people in the model. Is there predefined n, or you is flexible?
It's flexible. So during training, we fix the number of people so that we can perform batch training. But at inference, we set the batch size to 1 and consider all the people in the scene, and they all processed at the same time.
So the n decided by the height detection or people detection, by which one?
Sorry, what's first?
Is the n, the number n
Yeah.
is decided by people detection? Is that correct?
Yes.
Yeah. Okay.
Yeah.
Okay.
Thanks.
I have oh, go ahead, please.
You have a sense of which cues were typically most relevant for gaze following and which cues are not so relevant for gaze following, or is it all of the cues are relevant to different contexts?
Yeah, that's an interesting question. In general, I would imagine that cues involving more common interactions, which are more present in data, such as maybe talking and manipulating objects, might be more important. I don't have any quantitative results to actually indicate if certain cues were more important than the others. Maybe over here, so over here we did evaluate different sets of cues. So on the top, we have just 24 cues, here we have 117, and here 406. So in the smaller set of cues, it does contain many of the common cues that I mentioned, such as talking and so on, and it does not seem to help as much as having more cues. So maybe it's actually important to have subtle information regarding fine-grained interactions with other objects and people than maybe just common cues, but I'm not fully sure about this.
Can you speak to a little bit of the details of the in-context learning and how that was done?
Sure. Yeah. So for the in-context learning, we actually leverage the BLIP2 VQA model. So in this case, what we do is to provide the image with the red circle to the VQA model and ask it to provide just a description of the image and the person. So given now this image with a description, we provide both of these inputs to the VQA model and ask it a question. So over here, we actually have statements such as a person is class, and we convert this to a question such as is a person class. So given the context coming from the predicted description and the image itself, we then ask the question to the VLM, and then we get a yes or no answer, and this is converted to a binary flag. So then context learning comes from the predicted description of the image and the person.
Thank you.
Thanks.
All right, if there's no further questions, let's thank the speaker. So our next speaker is Takumi Nishiyasu.
Yes.
And he will be presenting on gaze scan path transformer, predicting visual search target by spatial-temporal semantic modeling of gaze scan paths.
Sure.
Hello everyone, I'm Takumi Nishias from the University of Tokyo. Today I will present our paper titled Gaze Campus Transformer, Predicting Visual Search Target by Spatial-temporal Semantic Modeling of the Gaze Campus. First of all, let me start with mentioning about the Yorba's work. In his work, it is revealed that eye movement is task dependent. In this example, we can see how eye movements vary when looking at the same painting, depending on the task given to the subjects. By analyzing these differences of the gaze campus, we aim to identify the task the subjects are engaged in. So in our work, we tackle the problem of estimating target object categories from gaze campus during the visual search task. These are represented previous methods for this task, and this method in this slide predicts the target category by using the histogram of semantic information at the fixation points. While this method is good and effective, it has some drawbacks. So the first one is the previous method focuses solely on the image features at the gaze fixations, so failing to incorporate the spatial temporal information of gaze campus. And second, the previous method lacks the mechanism for capturing the interrelationship of image semantics among other fixations. In other words, previous model uses the representation that doesn't contain information about eye movements and the information about the links between each fixations. So in contrast, our method uses a representation shown on the right. The representation obtained with our approach includes a spatial temporal information such as location and the order of the gaze fixation, as well as a relationship between the semantic features at the gaze fixation positions. Here is the basic problem setup of the visual search target inference task. In this research, we extended this problem setup to multi-task estimations. This now includes not only estimating the target categories, but also estimating the whether objects are present or absent, and estimating the correctness of the subject's judgments. This extension is suitable for the situation that we don't know whether the targets are within the images or not. And here is the overview of our proposed method. Our model combines the images and the gaze campus to predict the three aforementioned variables using the features created in 3 steps. So I will show the details step by step. So first, the model obtained the results of the panoptic segmentation from the input image. And second, the results from the panoptic segmentation and the gaze campus are sent to the embedding modules. These results are first turned into one-hot vectors and then into semantic features for each part of the images. And then 2D position information is added to the all patches. Finally, information about the order and the duration of the gaze fixation is added to the only to the patches at the gaze fixation positions. Following these embeddings, process the features are inputted into the feature mixer. This module extended the information between each feature through the mouse-head attention and enhancing the interrelationship among the features. Using the obtained features, the model estimates the category of search target and presence of target and the correctness of judgment. For training and evaluation, we use the Coco Search 18 datasets. These datasets contains eye tracking data collected while participants searched for 18 different types of objects. The images and labels in this dataset are everyday items from the MS Coco datasets. The dataset is composed of two types of subsets, the target present dataset and the target absent dataset. The target present dataset includes the images where the target objects are visible. In contrast, target absent dataset contains images where the target objects are missing. We combine these two datasets to create a situation where the model doesn't know whether the target is present or absent. So here are the performance results of the proposed method and the baseline on these datasets. In all metrics, the proposed model demonstrates higher performance than the baselines. And the main objective of this task is to achieve high performance on the target accuracy. But the proposed method also detects the presence or absence of the target and more effectively than other methods. And this is the confusion matrix of the baselines and the proposed method. Here we can also see the proposed method shows better performance compared to the baselines. And this is the result of the aberration study for effect of the gaze embedding. So overall, it's clear that each embedding has a certain degree of effectiveness, but not all embeddings have the same level of the effectiveness. And furthermore, the results show that including all embeddings is not necessarily beneficial. In conclusions, we propose the gaze campus transformer, a new method that predicts the search target categories from the image semantic features and the gaze campus. Unlike previous methods, our approach integrates the spatial-temporal and the semantic information from gaze campuses and improving the visual search target inference accuracy. So one limitation is that our method heavily rely on the datasets collected under specific conditions. So potentially introducing the biases into the model's prediction. Thank you for your listening.
We have time for a few questions.
Biases are you talking about?
Sorry?
Biases, what kind of biases are you talking about?
Yeah, it's only 18 objects in the ground truth table. So if the new if we want to predict the other category outside of these labels, yeah, our method fails. Yeah.
I have one question. So if you go back to your ablation study, I'm curious to understand a little bit what were intuitively the most important factors that actually did influence accuracy?
Yeah, at TDE and GSE mean the gaze related embedding, and PE means just the 2D spectral embedding. So all of the fixation, including fixation position and other positions. So these results show that the gaze related embedding is much have the good effects for the estimating the target, but including that these all features not so effective. Yeah.
Thank you. Okay, if there's no further question, let's thank the speaker. So the last talk is GES CAN, a dataset and method for gaze estimation classroom attention measurements. And it is being presented by Arshad Khan.
Right, thanks very much. Right, so I think mindful about the time because I'm the last one, so hopefully I won't take. But my name is Arshad Khan. I'm from a company called Ilm in Saudi Arabia. We are based in Riyadh and in London. We have been working on gaze estimation and gaze tracking for the last couple of years. And this presentation is more about just to even share the our experiences and based on those experiences, obviously what we have done just to present this GESCAM data set, which is about more kind of like making sense of the naturalistic attention levels in classroom. I mean, I appreciate that there's been lots of talks on the eye tracking face feature based extraction and other approaches. There have been 2 talks on the gaze following. I think this is the 3rd one. So we have been just struggling to pinpoint all these to compute the aggregate attention in a typical classroom. So, I mean, it's like of support in large scale data collection has been one of the issues. Obviously, we haven't tried any eyes tracking, but we are simply just trying the GTD, which is gaze target detection, to associate individual and their gaze targets. And predominantly, the issue is basically in the current classroom culture. There's lots of information overloading. So basically, interpreting or making sense of the attention level in the classrooms become even more difficult. The actual problem is basically from a 3rd person perspective, finding out where a person is looking at becomes a challenge. So the attention target detection videos and real-time RTSP, we have been facing issues because we have had a few deployments in various universities. We started off working with some local universities to collect data in real time and then to deploy this baseline application there to make sense of the classroom culture there, just simply using RGB camera. And those kind of things kind of informing us along the way that data insufficiency has been an issue, and that's what exactly led us to kind of like establish a synthetic data initiative permanently for various of our initiatives, specifically for gaze target attention in order to bring improvement. Obviously with the GTD solved the problem with the 2D, but the problem is when you use just one single camera in a classroom, that becomes a huge issue. So annotation and labeling, we struggle a lot with the annotation and labeling because it's so costly and time consuming. So we needed in order to support their kind of efforts to bring in more improvement. So existing approaches, it's 2. I mean, that's what I have made up from the prior art search. Is one focuses on the scene feature extraction, and the other is head feature extraction. The 3D gaze regression, GTD from 1st person view and the 3rd person view ignorance, there's like a huge gap between that. And then, so we need some sort of like rich contextual cues for gaze target detection, where we can pinpoint the gazes, the individual's gaze with the target in a particular POI, which is the point of interest. So where exactly we fit in, where does the GESCAM fit in, is to kind of like respond to that adaptable requirements in different classroom using 3D modeling. And I'm just going to show, so this is our previous work presented last year in Europe, which was mainly just looking at the projection of 2D images into a 3D perspective using depth-infused saliency mapping. So there we came up with quite good results with including the depth maps and the depth-infused saliency map and the MMF, which is a fusion of multi-model networks. But we did need more data, and that's specifically in with the depth maps with different kind of like classroom environments. So that's what led us to the GESCAM. So if I can just switch through, realizing of the time, is basically to tell you that synthetic classroom data has 60,000 images, 650,000 instances of students and teachers, the gaze estimation, attention measurement, and education technology development there, they've been focusing more on kind of like these tools which we have used to develop this just the data set within a couple of weeks. It's kind of like we call it GTD in the wild image, captured from third-person perspective. It's so different tools like blenders used to create different sort of like 3D models, different furniture arrangements, different characters, animation, and clothing to simulate the different clothing with different sort of like 20 different classroom environments. So if we just look at this, this is a more kind of like, if you can see, there is not only the angle differences, but the culture differences as well. We face initially issues with the people wearing scarf and those kind of spatial dresses in Saudi Arabia. So we kind of like had to train a special face detector, which was able to detect the heads from the back of the heads and the front of the heads, so that we can just keep into account the facial feature, the back of the head features, and then basically to map it out to the target of attention. And then this like shows you the scale of like the annotation in terms of the head, gaze line, individual, in order to pinpoint this to different individuals. So you see the depth maps, you see the bounding boxes, the mask, the scene mask, and the gaze line for different kind of like classroom all at the same time, simply just from an RGB image. This is just like a network architecture where we kind of like address it using two loss functions, the MSE and the angular, where we haven't considered in this network the depth map data as yet, but the scene and the head through modulation and the attention layer, we kind of like got the object attended head embeddings, which kind of end up in a heat map. The enrichment of this, so obviously this more kind of like the details, because the head embedding and seed embedding mask concatenation happens, and then the soft attention layer, and then the modulation, and finally we get the heat map. Basically, we tried that in different sort of classroom in real time so far in 2 different universities, and the results were quite obviously quite good. They were not amazing, but there's still like plenty of work to be done in that sort of area. And this is just the to sort of like evaluate it with in terms of like the predicted and the actual the ground truth. And to kind of like track the individuals, we it's like the color coding of the head boxes for the sake of like qualitative evaluation. So this is just the in terms of 3 metrics we use, the AUC and the Euclidean distance and the angular. So just come obviously, I mean, you can see there's a huge difference between the angular error and our angular error, simply because in the gaze follow and the video attention target data sets. Most of these gaze follow has been captured from social media and movies data sets, while in this typical classroom, obviously, when you look at the vector magnitude, that is more kind of like looking at more diverse kind of focal points, because the classroom culture is definitely different than what these mainstream network architecture has been trained on. We also consider for evaluation some of the prominent work, the last three. And the random method was used just to kind of create some random values and then to test different networks on them. And the center is obviously the fixation point when we assume that they would be on the center of the objects. And the three other works were evaluated, and we were coming up quite good in terms of performance in the gaze heat mapping. So I think just to wrap up, these are the currently ongoing use cases, which we are kind of like working on with the different clients. So the children attention estimation in classrooms, this is what we are working on a couple of schools. The two hospitals interested basically after having seen the earlier demos, they want to use the technology for ADHD detection among the two special needs schools there. And the consumer segmentation, the retail attention is there's a huge demand. Obviously, we've been contacted by various clients to kind of use the technology for retail attention and segmentation of the customers' shopping behavior. And currently we are working with further universities, with one in the UK to trial this technology as we work on. Then this is kind of like future work. So yes, cross data performance evaluation needs to be done, combining the depth estimation with the current network and the personalized attention estimation. That's what people are more asking about, especially from the education establishment and the few-shot learning. Thank you very much. I think I just wanted to show you some of the demos from our application that are currently being used using our gaze target attention technology. One is in the online classroom, the training centers there on the top right side, in the classroom in the bottom right side, and the events where a conference. We presented this in the LEAP conference in 2023 and 2024 as well, with a complete dashboard system whereby you can see a segment like a region-specific attention estimation within a specific site or a booth, where you can see basically the attention level keeps changing through the days and weeks. So that was kind of like some sort of like an achievement which were appreciated by the conference organizers there. Yeah, I think it was just started, but I think I'm running short of time, but otherwise I would have shown some videos, but I think I'm done with the time wise. Yes, more than that. Thank you very much for patience.
So we're running a little behind on our schedule. So I think right after this, we're going to end very quickly. Apologies, but I would request you to please ask your questions offline, the speaker. And but thank you for your attention. And so this concludes our session on all the accepted papers. Now we'll pass the ball on to Jing.
Okay, so now it's time to celebrate the winner of the workshop. So the order we have very carefully reviewed and discussed about the papers they presented today and submitted to the workshop. So the best paper award will go to the exploring the zero-shot capabilities of vision language models for improving gaze following by the Anshu Gupta, Pierre Card, Arya Farhode, and Jean-Marc Autobase. So yeah, this top award. You take photo.
Thank you so much.
Yeah.
Congratulations.
So this award prize is sponsored by NVIDIA, and the prize is GPU.
Oh,
card.
wow.
Yeah. Yeah.
We'll ship it directly to you.
Okay,
Yeah.
great. Thank you.
Congratulations. And also, thanks to all who participated in the best poster award, which goes to the Gaze Campus Transformer predicting visual search target by spatial-temporal semantic modeling of Gaze Campus. The authors are Takumi Nishiyasu and Yuichi Sato. Congratulations. Okay, and this award is sponsored by Google. So congratulations. Okay, so that's it for today's workshop. So thank you very much for attending this GAZE workshop this year. And hopefully we can continue our effort on fostering this GAZE research in computer vision domain. And the computer vision domain has been advanced very quickly and drastically. And to be honest, the GAZE research is slightly behind the phase. But I think we have huge potential because it's very much interdisciplinary research topic. And our community, GAZE community, is going to keep continuing, our exploration for further opportunities through this workshop. And we hope to be the kind of pivotal role continued. So thank you very much for coming, attending, and hope you guys enjoy the rest of the Sibopia.